All right. So today we're going to be talking about heap exploitation. It is the coolest exploitation. It's the most real exploitation we do in the course. It's a really exciting topic, so I'm keen to get into it. Um, I was doom scrolling on Instagram earlier, and I saw this great quote, and I think it sums up what I'm going to be teaching today. It says, "To study heap exploitation, we must learn the rules. To create heap exploitation, we must break them." Um, so pretty much today, it's gonna be a lot about, okay, what is the heap? How does it work? There's all these components, and we don't know exactly how they work, so we can break it and start writing our exploitations. So, okay, what is the heap? No, it's not the data structure. The heap I'm talking about is our memory management. So we've got two main functions. We've got malloc, which says, hey, give me this many bytes of memory so I can put a value in there. And we have free, which is, hey, here's a pointer to an address. I no longer need these bytes. You can get rid of it. All right, sweet. So here we've got an example, right? So we're declaring a bunch of pointers, and we're doing that through malloc. And let's do our first one. So when I'm thinking, okay, I want to write a malloc, well, I might just start at the top of the memory and work my way down. So I might go, all right, here's our first malloc. I'm just going to put these bytes here. Seems all right. And here I've got my top chunk. And this is how I can keep track of where I can allocate memory. Because if I know where the top is, I can just keep moving the top down and down and down. All right, so let's allocate our next bit of memory. We can move top chunk down. Our next 16 bytes, move our top chunk down. And our next 40 bytes, move our top chunk down. However, you might see there's a problem here. The first problem I want to mention is that some values in C want to be 16-byte aligned. Oh, what does that mean? Well, each of these boxes here is 8 bytes. So let's say I wanted a byte that was 16 bytes, a value that was 16 bytes aligned. I'd want it to start here and end here. So, okay, that works for this one. But then the green one, it would start here, and then it would cut itself in half and move the rest of it over here. That's not very good, because some instructions only work when the memory is 16-byte aligned. So we want to make sure that our malloc always returns 16-byte aligned pointers. So, okay, let's change this. So now they're all 16-byte aligned. We see they're all next to each other. And now I can finally free my pointer 0, which is this one. But hang on a second. All I have an address. I'm saying free 000, right? I've highlighted all these numbers in red because when you look at the heap, there's going to be all these numbers and you're like, what's going on? I mainly just look at the last 3, and that's how I reference it. So I'm saying, okay, free 000. Okay, does that mean I free 8 bytes? Does it mean I free 16 bytes? Does it mean I free, well, here we've got 40 bytes. Do I free 40 hex bytes? Well, I don't know how big this chunk is. So we can add a size. That's what we'll do. So here I'm saying, okay, we've got 8, 10, 18 bytes in hex. Here we've got 8, 10 bytes in hex, right, where the 1 is 16. So 16 bytes. Here I've got 8, 10, 18, and so on and so on. But you see, okay, now I've got a lot of this wasted space. Let's fill that in. And of course, now we need to adjust the size again. And oh wow, when I allocated 16 or 8 bytes, or 16 bytes again, these are the same, I always get a size of 20 hex bytes. And okay, so I'm going to free it. The way I think about freeing is that we're putting it into the bin, right? We're done with it. I no longer need this memory. Bam! Into the bin. And now we've gotten rid of it. But eventually, we probably want to put memory back up here again. How can we keep track of where we've got these free spots in memory? Well, we have these things called bins. So here is our tcache bin. It's got a count and an entry. And you can think of the entry as the head of our list. I mean, there's nothing in the list, but we just freed some memory. So that's going to be the head of our list. So here is our head. We've got 050, and 050 is here. And when we add it to the list, well, here's our next pointer. So remember the next pointer, well, there's nothing else in the list, so it's null. And the thing about C memory and our malloc is we want it to be fast as it can be. We want it to be super, super fast memory. So if this is our linked list, do we want to insert at the head of the list or the tail of the list? Well, if we insert the tail, let's say there was 5 things in here, I have to go 1, 2, 3, 4, 5, and then insert it. Or if I insert the head, I can just go 1, change this value here, and it's inserted. So obviously we're going to do first in, first out. I insert it at the head, and I take it from the head. So here, if I freed another thing, well, I'll change its entries to the 90, and then this next value would point to, well, our previous freed chunk. We keep doing this like so. All right, that seems to make sense. But I've got a question. What if we had a bigger chunk? Should it go in the same list, or should it have its own list? Well, let's think about it. The point of this list is so that when I want to allocate a new chunk, I can quickly reuse other chunks. So let's say I wanted 20, well, I go to this list and, oh, I found a chunk that's size 20. If it was size 50, I'd have to go, ooh, 1, 2, 3, oh, I found size 50. But what if I didn't find size 50? What if I searched through this whole list and there was no size 50? Well, that would be a big waste. So what we actually do is we have this little entry for all sizes. So this is for all the chunks that are size 20, and this is for all the chunks that are size 50. So this is what it looks like in our memory, okay? We have this thing we're gonna call the T-cache per thread struct, and what we're gonna have is gonna say, okay, I've got 3 entries in my list, so I've got 3 items of size 20, and it starts at this address. So I go to this address, and the next one, or the next one is points at 090, 090 CR, and so on and so on. So now, if I want to malloc a chunk, instead of taking it from the top, it's going to check our free list. So it's going to say, hey, oh, I've got 3 things in my T-cache bin. Let me get one of those. So it's going to say, oh, okay, this address here, that's the head of our list, 070. I'm going to return this address to the user, and they can start writing their data there. So, okay, our head has to be replaced. Remember, this is the next value. So we're now saying its next value will be the head, which means 090 is going to be our head. And now we've only got 2 things in our list. And of course, now the user can go and write whatever they want to that chunk. So I'm going to write the mark 87. I'm going to say we are a teacher, and we're keeping tracks of students' marks. Okay, let's malloc another chunk. Well, I see, okay, I've got 2 things in my list, so I can check my list. And here I'm going to return this pointer. This is the head of my list. And I'm going to put our next value into here. It's going to become the head. So 050 is now the head of our list, which means this chunk right here. And we've only got 1 thing left in our list. So now if I want to do another malloc, well, I'm going to say, oh, I'm going to return this address to the user. So I'm going to return this chunk, and its next value is going to be put in here. So I go, hey, I've got 1 thing in my list. I'm going to return this to the user, and then our next is null, and we've got 0 things left in our list. So now if the user wants to malloc 1 more chunk, well, it's going to take it from the top, like so. I think that seems to make sense. And it's going to return this address to the user. And they can then write another value, like 95. Oh, they've done very well. But, okay, when we're doing this, we notice that where we're writing our mark, and where our next chunk is in the list, well, they're at the same address. They're pointing to the same thing, our malloc in our program, but they're seeing different things. The program sees, here I can write a mark, and malloc sees, oh, here's our next chunk. And remember, these values, they're all just 1s and 0s, right? So this string of 1s and 0s, it could be this number, it could be this address, or it could be this string. Okay, so they're sharing the same address. Could something go wrong there? Well, let's go back a second. Okay, so remember, here we've got a list of 3 things. All these chunks have been freed. Okay, what if this is pointing to this address? This is the head of our list. But what if we use this chunk while it's free? We call this a use after free. It's meant to have been freed, but we're writing a value here. Well, when we malloc a chunk, this value, well, this is meant to be the next pointer, so it goes to the value where the next is. Now, if I malloc a second chunk, well, it's going to point to somewhere over here. It's going to make a chunk where we said our next value was. And this chunk is on the stack, which means our user can now write to the stack. So let's see what happens. So here I've got some code. I've got a struct student, and they're going to have a mark. And then I'm going to make a struct student Morgan. This is going to be stored on the stack. Morgan's mark is 72. And we're going to be in this loop until we change Morgan's mark to a high distinction. Ha 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 ha. I'm going to print a menu. I'm going to make a selection. I can either make a student, set a mark, read a mark, or delete a mark. So let's have a look at that. So I'm going to go /marks and see, oh, Morgan's struct is at this address. His mark is 72. Okay, let's make a couple students. So I'm going to make student 0, and I'm going to make student 1. And let's see, what's happening in our chunk. So we can go to GDB, and I can say, okay, p-a. I see the marks process is running, so I'm going to attach to this. And if I go viz shows me the chunks. So here we've got what I had before. I have a chunk of size 20, and then at the moment I haven't set any marks, another chunk of size 20. Okay, let's try set my student 0's mark and see what happens. So I'm going to continue. So I could go B, enter student number, okay, 0, and set their mark to, let's set to 8. They've done really bad. Okay, now if I visualize my chunk again, we can see, there's now an 8 here in the mark section. Okay, but we want to try and do a use after free. We want to get this into the free list, and then malloc a chunk so it points into the stack. Okay, so let's free our students. So first I'm going to delete student 0. I'm going to delete student 1. Let's have a look what our stack looks like. Okay, so here is our big stack struct. So I can see I've got 2 things in my free list, and the head is B40. So I go down to B40. Okay, this is the head of our list, and its next pointer is going to be B20. So B20 is up here, and we can see, its value is null. All right, so let's try and change this address to be something in the stack. Well, we had a stack leak up here, and now let's put that into our Python and find out what its value was. Okay, so it's the mark of 1000, well, not 1000, 140724123928560. Big mark. Okay, so now I'm going to set the mark, and then I continue, of student 0 to be this really big number. Okay, and now let's look at our heap again, and we can see, okay, now we've got this big, this address has now been written into here. So that means eventually, if we keep allocating, we should get an chunk at this address. So let's make some more students. So I'm going to make student number 2, student number 3, and let's have a look at our chunks. So we see, okay, we've created 2 students. So now these has been allocated and this has been allocated. It looks a bit confusing because the chunk data is still there. And we can see we now have our heap address here. So now if we make one more student, what's going to happen? A4. Let's have a look at our viz. Oh, we have a new chunk here. Why did that happen? Well, if we look up here, remember, we have zeros here. We're saying we've got 0 things in our free list. But we do have a value in our free list. Oh no. What's gone wrong? Well, we had something like this. We had 2 items in our free list, and then we overwrote this address to forge a chunk. Then we malloced, and we malloced again, then we had 0. Oh no. So whenever it went to malloc something, it didn't realize there was something in our forged chunk. It thought there was nothing left in our list of free chunks. So what can we do instead? Well, instead of overwriting this one, we should overwrite this one to our stack address. That way when we allocate, and we allocate again, we're going to get some memory, which is full of values on the stack, and we can then overwrite it. So when it gets to the stack, it's going to write its size here. Then we as a user can write whatever we want here. We can write some mark. Okay. Let's try that out. So I'm gonna start again. And let's try. So dot slash marks. And I'm going to go to GDB again. Oh, this one. All right, so we need to make two students. Make student 0, student 1. And now we want to delete them again, right? So we're going to delete student 0 and delete student 1. Okay, look at our chunks. So this one is student 0, is the first one that was allocated. And this one is student 1. Which one is the head of our list? Because remember, if you look back here, you want to overwrite the head. Well, this one is pointing to null. That's the end of our list. This one is pointing to head. So you want to overwrite student 1. So let's find out what student 1's mark would be. So we need to turn this hex address into an integer. So we can go here again. We have a new integer. Now I'm going to set the mark of our student 1. And we are using it after we freed it, right? We should not be able to write to this address, but we are. Okay, and now if I look at my chunks again, this next value is pointing to here. So let's start allocating some students. So we're going to go continue our code. We're going to make a student. We can make them student 2. And they should just be given this chunk, right? And now if I look at my bins, for example, which I could have shown before, our tcache bin is pointing straight into the stack. Okay, and if we look up here, if I go viz, we can see it's saying we've got one thing in our free chunk list, and that next pointer, it's in the stack. So that means we make one more student, they are going to be in the stack. Okay, so we're going to make a student, call the number 3, and now this student's pointer is inside the stack. So let's look at that. Go viz. I actually have an array of the students up here. We can see, okay, that's a heap address, that's a heap address, that's a heap address. 0, 1, 2, 3 is in the stack. Now what are we trying to do? Well, Morgan's mark is there. At the moment it's 72, but I want it to be 95, let's say. So I'm going to continue, I'm going to say, okay, set mark of student 0, 1, 2, 3. I'm going to make it 95. Wow, Morgan's mark is 95. That's really cool. So we've successfully written onto the stack from a use after free. Wow, that's pretty cool. So why does this work? Well, pretty much we're trying to get these memory pointers to overlap with each other. So to begin with, we had this item in the free list, and we had our mark, right? We had this stored in our array. So we could still write to this free list by writing to the mark. We could do our use after free. We shouldn't be able to write the mark here, but we're still able to use this memory address here. And then after that, well, we had Morgan's mark. This is what my code saw. But it also had the idea that we've marked a new chunk here, and it's going to have, well, not student 1, it's going to have student 3's mark. So now both Morgan's mark and student 3's mark was in the same location. So when I wrote student 3's mark here, well, it overwrote Morgan's mark. So we've overlapped these chunks. And this is what we always want to do in heap exploitation. We want to overlap these pointers so that when they are writing somewhere, it's also affecting another pointer that sees it differently. So how else can we get this overlap? Well, what about a double free? If I free pointer 1, and I free pointer 2, I free pointer 1 again, well, now I've got this address in my array twice. And of course, this is going to loop back here because as this value changes, this value changes. It's the same memory. Okay, so what if I go, well, 0.1 equals malloc? Well, I'm going to get my first address from the list, 050. The second one is going to be 090. And my third one is going to be 050 again. Which means pointer 1 could be pointing to an integer, pointer 3 could be pointing to a function pointer, but they're both the same address. So when I changed, if I could write to an integer, maybe by doing that, I could change a function pointer. Or maybe we just do one alloc, and now, well, we have one pointer, which is going to be 050, right? And that chunk is also in our free list. And this looks very similar to our use after free. So that looks pretty cool. Let's try and hack that. Because now, well, we can change that address to another stack value, and maybe we can allocate a chunk at this address. Let's try.